fundamentals of fabulous flow. For your microphone, your speakers, to hear the audio through your PC, just click connection and select computer and then join. If you have any questions during the presentation or after, if you'll enter those in the Q&A section to the bottom right, we'll be able to answer the questions throughout the presentation and also at the end. Additionally, a recording of this presentation will be emailed to you at the end. You'll also receive the slide deck when we send the email, and there'll be a short exit survey to get your feedback on this so we can help improve our presentations throughout this webinar series. If you do have any questions later on that you would like to send us, you can send those to webinars@us.yokogawa.com. My name is Chris Koslow, and I'll be your host today. I've been with Yokogawa for 34 years in the instrumentation division. Our presenters today are Paul Warburton. He has a BS in electrical engineering, and he's been with Yokogawa over 32 years in various positions, including flow product management, field instrument leader, and he's currently serving the role in field application sales specialist. Also, Jim Levine, he's the owner of Classic Controls and has 30 plus years. He has a bachelor's degree in chemical engineering, and he's a Yokogawa representative for products and for systems. Before the presentation begins, I'd like to invite you to our Why Now event. This is Why Now 2024. It's going to be in Houston, Texas, October the 28th through the 30th. If you'd like to learn more information about this, you can scan the QR code on the screen, or you can visit us at yokogawa.com to find out more information and register for this event. In today's agenda, we'll learn about the top flow meter technologies. We'll review the theory behind the flow measurement and discuss common applications and challenges. We'll also evaluate the different technologies when selecting a flow meter, so you know how to choose which flow meter for your process. Lastly, we'll review the best installation practices for successful measurements. At this time, I'll now turn it over to our presenters, Paul and Jim. Paul?
Thank you, everybody, for coming today. Today, we're going to hit on some of the more popular flow technologies. There's a lot out there. We're going to focus on magnetic flow meters, vortex, Coriolis, variable area meters, talk a little bit about DP flow, and then ultrasonic.
Yes, and Paul, just to chime back in, as Paul mentioned, those are a subset of the available technologies that are out there. We've selected these because they're probably the most common and most trouble-free and most applicable. As in all flow measurement technologies, you will be asked a series of questions. You know, is it for steam, liquid, or gas? Is the fluid conductive, non-conductive? Is there a slurry? Is it heavy viscosity? What's the static pressure? We don't aim to ask these questions to cause you pain and grief. We typically ask these questions to pare down this list of available technologies to the most appropriate one. So just go ahead, Paul.
So the first we're going to talk about is a magnetic flow meter. Mag meters came out back in the 1940s, 50s timeframe. Yokogawa introduced our first magnetic flow meter back in 1955. And you can see there's been several family iterations along the way, all the way up to our new, or our latest, I should say, AdMag TI family, which consists of three meters within the family: the AXG, which is our more common technology, our more common meter; the AXW, which is geared for the water wastewater market; and then the AdMag CA, which is a capacitance type meter for low conductivity measurement. So how a mag meter works, it's based on Faraday's law. And Faraday's law says that if you have a magnetic field and you have a conductive process breaking through that magnetic field, you get a voltage potential output. So in a mag meter, if you look at the illustration in the upper right-hand corner, you have two coils, one at the 12 o'clock position and one at the 12 and 6 o'clock position. So as power is applied to the coil, you have a magnetic field running through the meter. If we look at the illustration on the lower right-hand side, you'll see two measuring electrodes, and they're positioned at the 3 and 9 o'clock position. So when power is applied to the meter and we have a magnetic field throughout the meter, and we have a conductive process breaking through that magnetic field, the voltage potential is being picked up by the measuring electrodes, and that in turn is proportional to the velocity of the meter. So that's why it's important when we program the meter to know what size it is. If it's a 2-inch meter, we make sure we have to put a 2-inch, tell it it's a 2-inch meter, because we're calculating the velocity by the area of that 2-inch to come up with a volumetric flow rate in gallons per minute. So when mag meters were first introduced, back in the 50, 60 years ago, 70 years ago, the type of excitation method was AC type excitation. And this was basically taking a meter and plugging it into the wall. So you had 120 volts AC, 60 hertz, and it was a good measurement, very good for slurry applications and fast response applications. But because it was an AC signal, we had very poor zero stability. The accuracy wasn't very good. It was a percent of span device. And then on top of that, it was high power consumption. So years later, pulse DC was introduced to the market, and this improved the power consumption, improved the accuracy from a percent of span to a percent of flow reading, and improved our zero stability. But because of the low frequency, the response time wasn't as good in those slurry and batching type applications. So Yokogawa introduced the dual frequency excitation, which is standard in every meter we ship today. And that incorporates two pulse DC signals that are superimposed on one another. One's about 6.25 hertz, one's around 75 hertz. And it basically gives you the best of both worlds. Very fast response time for your slurry applications, good zero stability, high accuracy at 0.3% of your flow reading, and low power consumption. And if you were so inclined, if you want to hook an oscilloscope up to the device, you can actually see the low frequency and high frequency and dual frequency components.
So at the end of the day, where does dual frequency and what benefit does it provide the customer? I will tell you that I've been doing this for almost 40 years, 34 years as a Yokogawa rep. Any slurry application, what you see is a more of an effect on the slurry noise at the lower the frequency component than on the high frequency component. So very often people cure this by just increasing the dampening, which for process control people drive people nuts. This is actually a chart off of a zinc bead flow loop. And you can see the difference and the improvement that you get with dual frequency on slurry noise.
So magnetic flow meters are liquid-only meters. As Jim mentioned early on about the different processes, for mag meters, it has to be a liquid and it has to be a conductive process. Mag meters have a minimum threshold of conductivity, typically down to about 1 microsiemens of conductivity. We do have our AdMag CA, which I mentioned is a capacitance meter that we can get down to 0.01 microsiemens of conductivity. That's for DI water applications. Another huge benefit of a mag meter is that there's no pressure drop. So whatever pressure drop calculation you're doing for a piece of pipe is the same that you would use for a mag meter. Wide offering in sizes from 0.1 inch up to 72 inch units. As far as materials are concerned, we have the electrodes. So we have stainless steel, alloy 20 equivalent to Hastelloy C, tantalum, titanium, platinum iridium, tungsten carbide. So a lot of different materials for whatever application you will need. So mag meters are used in pretty much every industry, as you can see, pulp and paper, food and beverage, chemical, steel, power, water, wastewater, from very basic water applications to very aggressive chemical, corrosive applications, heavy slurries in mining and pulp and paper. So it's a very well-rounded meter for a lot of different applications.
Yeah, in some of these industries, these are real pictures from food and beverage. In this, you can see you have some tri-clamp connections. You also see in the second photo from the left a blue cable. The food and beverage industry and some of the water wastewater markets are calling for Ethernet IP interfaces. So we've got that base covered. On the top right is a picture of a batching system, which is a combination of Coriolis meters and mag meters. Coriolis meters we'll get to in a second, measure mass and density. For basic water batching, people were fine with using mag meters. But end of the day, this is kind of representative of what goes on in the food and beverage marketplace. Now, the second industry or example we picked is a very aggressive. Not only is the dual frequency aspect of the product applicable in pulp and paper because you're dealing with a lot of slurries, we make two types of flow tubes. We make a PTFE, which is a generic, pretty common flow tube construction compared to everybody else. However, we make a mechanically retained PFA liner, which we've been making for a very long time. And at the end of the day, that grid in the center is actually welded to the meter body, and the grid retains the liner, not the piping system, not the meter body. So this is very common in an aggressive application. This is the AXG flow tube construction. And bottom line, we put these on blow lines on K-meter digesters and batch digesters, and it's a wonderful mechanically retained aspect to the product. I will also say that a lot of these technologies have the ability to do inline verification, meaning you can check the health, you can detect coating on the electrodes, you can check performance compared to the original factory delivery, and this product has that feature as well.
So next we'll discuss the vortex meter. So Yokogawa released our first vortex to the market back in 1969. As you can see, we've had several families along the way, and our current family offering is the VY series vortex. So how does a vortex meter work? It's based on the von Karman principle. And what the von Karman principle basically says is that if you have a fluid coming down the line and you have a bluff body or shutter bar in the line, as the fluid hits that bar, the flow is going to shear off at an alternating rate, creating vortex formation. So if we were able to measure the pressure inside that vortex, you would see that it's a lower pressure compared to your line pressure. So with our shutter bar, so we do it a little differently. We put the bluff body and the piezo crystals all in one device, which we call our shutter bar. And you can see the illustration in the bottom right corner. So our shutter bar contains two piezo crystals. And what these piezo crystals do is convert a mechanical stress to an electrical pulse output. So as flow is hitting the shutter bar and vortices are being generated, you have a low pressure vortice on the right side, your higher line pressure on the left. So it's going to want to physically stress that bar from the left to the right. It's putting a stress on the crystals, which in turn are giving us a pulse output. When the next vortice is formed on the other side, that high and low will swap, and again stressing the bar and giving us a pulse output. So every time a vortice is formed, it's stressing the bar and giving us pulses, and those pulses are directly proportional to the velocity of flow. So I like the visual learning aspect of things, and with this example here, we look at a flag on on a light breeze or no wind day, the flag is just sitting there, not moving much. As the wind picks up a little bit in the middle picture, we have a little bit more of a stiffer breeze. You get some movement in the flag, but it's not a consistent and repeatable movement. But then on a very windy day, that flag is moving and rippling back and forth and at a repeatable rate. So if we take that illustration and we look at the vortex meter, the illustration in the upper right-hand corner on the right-hand side, as flow is coming down, hitting the shetter bar, it sticks to the contour of the bar and continues down the line. So in this example, we're looking at a low flow, low Reynolds number, below a 5,000 Reynolds number. In the middle illustration, the velocity increases a little bit. So we get some vortex formation, but not very consistent, a little repeatable. But we're able to measure this, and we have a little bit higher velocity, and that equates to about a 5,000 to 20,000 Reynolds number. But then as flow increases, we get good vortex formation at a repeatable rate, and this is a value above 20,000 Reynolds number. So this is where we want to be in vortex measurement. So the vortex meter is a very good meter if we have a set range of flow. This isn't the meter we want to choose if you're looking to measure down to zero flow, because as you can see in the top illustration, we could have flow, but just not enough velocity to.
Okay, stand by.
So vortex meters are great for liquid, gas, and steam applications. In liquids, we like a clean process. Low viscosities are ideal, but we can do a high viscosity application as well. We have our sizing programs, and basically with a high viscosity application, it limits the vortex formation. So if our velocity is high enough to overcome the higher viscosity, we may be able to measure it. So we don't want to shy away from those applications with a vortex, but it's best to contact us and let us run our sizing program and see if it'll work or not. Any materials that are processes that are compatible with 316 stainless steel or alloy materials, which is a Hastelloy C equivalent. We have high temperature up to 842 Fahrenheit. We can also do cryogenic fluids. Gas and steam, again, no problem as long as it's compatible with the materials. But we also have multivariable options. So within the shutter bar, we have a built-in RTD assembly that can measure temperature. So for saturated steam, we have the built-in steam tables to give us a saturated steam measurement. If it's superheated steam or a gas application, with the VY meter, we can take an analog input from a pressure transmitter and do the math inside the vortex head to come up with a compensated mass flow for steam or for gas.
Yes, as you can see here, personally, everybody develops a favorite technology for a particular application. I prefer vortex meters for steam service, and to Paul's comment, if I have varying pressures, then I usually go multivariable. It's a direct linear measurement to the flow, so typically compared to other technologies, you have better turn down, but it is outstanding as a steam meter, and we can also handle high temperature steam as well.
Yeah, it's a good meter. One of our engineers, when I first started, taught me that this is a great meter and was developed around a boiler. So you have water going into a boiler, you have natural gas going into the boiler where you can use the vortex meter, and then you have steam on the outlet side. So very well-rounded meter for a wide range of applications. Next, we have the Coriolis meter. So the vortex and the mag meter we just spoke about are velocity type flow meters to get volume flow. The Coriolis is a mass flow measurement. Now, when I was a little kid, my my dad asked me what weighed more, a pound of bricks or a pound of feathers. And being 5 years old at the time, of course, I said a pound of bricks. But the reality is it's a pound, right? The mass is the same. If we took a brick, a pound might be a little bit bigger than the size of our cell phones, maybe a little bit thicker. So small volume area, but a pound of feathers would probably fill up a 12 by 12 room. So you can see the mass is the same, but the volume is completely different. So when we're looking at flow measurement, in this illustration here, the mass is the same for both, but as temperature increases, our density will decrease. And then in turn, the volume of that liquid will increase as well. So you can see the density is changing, but again, the mass remains constant. So here's a little example you can try at home on the Coriolis to see the Coriolis effect. So if you took a garden hose and laid it out in the yard, turn the valve on, and make sure your nozzle is closed on the end so there's no water flowing through it. Pick the hose up in a U shape, as you can see in the illustration, like you're going to jump rope, and start to rock it back and forth. And then have somebody open up the nozzle so the water is now flowing through that hose. And as you're swinging it back and forth, you'll feel the twist of that hose from your left hand to your right hand, and that's the Coriolis effect. So within the Coriolis meter, we have we utilize a dual bent tube design. So there's two tubes that the process is going through. And if you look at the cutaway picture on the left, you'll see an oscillating pickup that resonates the tubes at a set frequency. And then on the inlet side and the outlet side, we have our pickups. So if we fill the flow tube with a liquid and we close it off, put valves on each side, the pickups will have a sine wave that's in phase with each other. But the minute that we open those valves up and flow starts to flow through the meter, we'll see a phase shift between the inlet and the outlet pickup. And that phase shift is proportional to the mass flow measurement. So a Coriolis meter could also measure density. So we have a known frequency we're oscillating the tubes at. So if the density increases, this will cause the frequency to decrease, and vice versa. As density goes down, the frequency will increase. So not only could we measure mass flow, we can also measure density with the Coriolis meter. And then internal to the Coriolis, there's an RTD assembly, and depending on the size meter, it could be in on the flow tubes, mounted to the tubes themselves. It could be mounted to the flow splitter as the flow is going into the meter. But this is a third variable you can get out of Coriolis. So we can get mass flow, density, and temperature out of one flow device. And then by utilizing the density and temperature, we can do more advanced measurements like a concentration measurement or net oil and gas void fraction measurement. So again, the Coriolis is a mass flow measurement with a very high accuracy of 0.1% of your mass flow. So Coriolis also has a wide range of applications, liquid, gas. We can do superheated steam, high temperature applications. We do cryogenic applications. Viscosity is not an issue with the Coriolis. Very large turn down, so we can get almost down to zero flow compared to the vortex where we're limited there. We'll see in a little bit on the flow conditioning side, but on a Coriolis, you don't need any upstream or downstream piping requirements. So that is a big benefit as well on the Coriolis. And we can do multiple fluids in the same pipe. So with the concentration measurement, if we're measuring proof alcohols, has alcohol and water mixture, or a glycol and water application. So we can do multiple fluids within the same pipe, in the same meter. And then the sizes are, the smallest tube size is about the tip of a ballpoint pen, so less than a millimeter in size, and up to about 12-inch in line size. So this is an application we do for at a wellhead. This is what we call a lease allocation meter. So you can see the Coriolis in the forefront, and then the tank behind there, that's a separator. So as the process comes out of the ground, the oil, and it's not just oil, you have oil, water, sand, rocks, gas, everything that's coming out of the ground goes through a separation process. And that separator there at that point is separating the liquids, the oil from the water. So if you're a customer and you're coming to buy oil, you want oil. You don't want oil. You don't want to pay for oil and get water. So what this lease allocation meter is doing is determining if there's water in the line. So in the separation process, sometimes the valve will stick. Sometimes the flow is just coming in too quickly, and it's not giving it enough settling time to separate out the oil and the water. So it'll dump over. You'll get both water and oil into the oil side of the separator. So by taking well samples of the oil and a sample of the water, we can come up with density coefficients to program into the Coriolis meter. So at this point, we can determine what we call a water cut or net oil measurement. And then to take it a step further, if that density goes below the oil, that's considered to be gas void fraction. So we can also determine the amount of gas and train gas in the line.
So we were asked to keep this under an hour, and we could take any of these topics and probably go pretty deep with it for 3 or 4 hours. My experience has been most people go to Coriolis meters if it's liquid service because the fluid is non-conductive, and they may calculate volumetric based off the mass and the density, but the other driving force is whether or not it's a custom. So it's a recognized technology for bill of lading purposes, both in liquid and gas. So this is a couple pictures of that. We also can do inline blending. So very often people will blend things in a tank. We've done inline blending for diesel enhanced fuel, KOH, just to name a few, HCl, where you're actually blending to a certain concentrate, the Paul's comment, directly into a truck for custody reasons. Again, back into food and beverage, you'll see a variety of meters used for batching purposes. It's very common there. As Paul alluded to, viscosity is not an issue. Generally speaking, you emphasize these meters based on flow, viscosity, and available head pressure. And just to elaborate on Paul's comment, zero straight run required.
Excuse me. So next up, we have the variable area meter. This is a very, very old technology and also known as a rotometer. The original variable area meter was developed by a company called Rota over in Germany well over 100 years ago, actually 1909 to be exact. In 1995, Yokogawa acquired the Rota Corporation. And so now the rotometer is part of the Yokogawa family. And since then, we've made some enhancements to give you a heart with an analog output, trophy bus, foundation field bus, and explosion-proof offerings as well. So again, Rota was the founding company of the so-called rotometer, variable area meter. But today, most people know this as a rotometer. And it's just the brand name of the product that we have, and it's part of the Yokogawa family. So how does a variable area meter work? Now we have a conical tube or cone, and then inside that we have what we call the float. So it's important to know that the rotometer has to be installed in a vertical installation, and flow has to be in the up direction. So as flow is pushing up on that cone, or I'm sorry, on the float, it hits a point of equilibrium, and that tells us what the flow is. So there's two types of rotometers. There's a glass or plastic type and a metal type. And on the glass type, as that float goes up, the scaling is printed on the glass part. So you would look at the top of that float, and that would be your flow rate compared to the scale. In the metal type, we're magnetically coupled to a pointer, and as flow is changing, the scale is changing, or the pointer is changing, going up the scale. So it's all visual measurement. So one of the benefits of the rotometer is that there's no external power. They're typically used for visualization. Can be used in any type of applications, liquid, gas, steam. Doesn't matter if it's conductive or not. It just has to be a clean process. They're very easy to install with minimal maintenance. And when we size up a rotometer, the pressure loss is, even though we have that float in there, the pressure loss is on the low side. So rotometers are everywhere. Most of us have been to the hospital or to visit people or in ourselves, but if you've ever seen an IV drip bag, there's the little controller on the outside of that. That's a rotometer. That's in non-industrial. In the industrial side, we have sampling systems. So this is a gas monitoring sample system, and you can see inside the panel there's a number of rotometers. And again, it's just for visual indication and control of the amount of gas going through the system. So next we have DP flow. So DP flow consists of two sections. The first is the primary element side, and the primary elements can be orifice plates, pitot tubes, venturis, V-cones, accellibars. So there's a lot of different types of primary elements used to create a different differential pressure. The secondary part of it is the transmitter. So the differential pressure transmitter is sensing that differential pressure that's created from the primary element. So if you have a simple basic water application, you can put a standard DP transmitter on there, set it up for square root, and it'll do the math for you to give you a volumetric flow. If you have a gas application, you can use a multivariable transmitter across the flow element, and the multivariable will give you a differential pressure, static pressure, and a temperature measurement to correct for changes in temperature and pressure for compensated flow to get you a standard cubic foot value. So DP devices are pretty simple devices. Not an orifice plate. There's not much to it. It's just a plate. It's installed with the transmitter mounted across it. Can be used in pretty much most applications, liquid, gas, and steam. So, comparing to the other technologies, it has a financial advantage, especially on the smaller or on the larger sizes. I mean, and it's maintenance-wise, it's pretty much the same as a transmitter. Whatever typical maintenance you would do on a pressure transmitter is what you would typically apply to the DP device. So this is an installation of an accellibrar, and this was a gas application. And you can see there's not enough, or not a lot of straight run upstream or down. And with the benefit of the accellibrar is that we don't need a lot of upstream or downstream piping. So in this particular installation, it was a natural gas, and we were just measuring the differential pressure, and there was an external device to do temperature and pressure compensation for the natural gas.
So ultrasonic technology can really fall into two different technologies in terms of what's being used, Doppler or transit time, and two different types of products. There is a clamp-on technology that exists, and that is where the piece of pipe is actually used as your flow element, And then you have something called wetted transducers, which are actually formed in a meter body manufactured by the company. Both these technologies can measure gas and liquids. The clamp-on technology, or the Doppler technology, is essentially how the policemen back in the old days used to catch us from speeding. They would shoot a frequency downstream as the car approaches. The car would reflect that frequency, and the shift of the frequency received was directly proportional to velocity. Typically, that was reserved in the old days for dirty fluids. Transit time technology, that is, as a transducer that each has a transmitter and receiver in it. And one transmitted signal into the flow path is going to be slowed down by the flow path. The other transmitted signal going in the other direction is accelerated by the flow path, and you're measuring delta time. I will say that the transit time technology has really come a long way and really probably takes care of 90% of the applications, even in sewage these days. So really when it comes down to it, again, you have clamp-on technology where you're using a piece of pipe as your flow element. It's got a convenience to it because, hey, you don't have to cut the pipe. You can do small pipes, big pipes. However, you need to know the construction of the pipe, is it lined, all that good stuff. I will say that the wetted ultrasonic technology is approved for custody transfer, both on liquids and gas, and it has the benefit of being able to being able to pig the line. There's no obstruction, so you can actually pig the line. So basically, that's kind of a simple explanation of how ultrasonic works. And as I said, at the end of the day, there are the benefits. And that's a picture of a clamp-on. And like I said, they can handle high temps, regular applications, but end of the day, that piece of pipe that you're reading through is your flow element.
So we just talked about several different technologies. So the $1 million question is, which one do we choose? It would be nice if we had one flow meter for all applications, but that's just not the case. So the questions, as Jim mentioned early on in the presentation, these are the questions that we're going to ask. When you have a flow application, is it a liquid, gas, or a steam? What's your flow rates? Basically all your process conditions: pressure, temperature, density, viscosity. If it's a liquid, is it conductive? If it's a conductive process, then we may want to look at a mag meter because that's best suited for those applications. If it's not conductive, then we can look at a vortex meter or maybe a Coriolis or DP flow or ultrasonic. So there's, this is why we ask all these questions. Same if it's a gas. If it's a gas application, then we can't do a mag meter. Do you want a volumetric flow or mass flow measurement? What's your line size? What's your flange ratings? We've hit, a lot of us that have been doing this for a long time, we live and we learn, and sometimes we assume, flange rating for me, I learned the hard way. We sized up some meters based on the process conditions, and 150-pound flange was perfectly fine, and that's what we went with. Well, when the customer received the meters, they told us that their process was rated to 300-pound ANSI. And we shipped them 150-pound flange units because we never asked them what their flange ratings were. So the unfortunate part is you get burned a little bit here and there, and that makes us learn down the future that, for the future, to ask a lot of these questions so we don't get hit again. So again, which one do I choose? What type of accuracy are you looking for? What type of turn down? Do you need to get down close to zero? What type of installation do you have? Do you have proper upstream or downstream piping? What's your materials? Do you have exotic materials, or is it straight, stainless steel or carbon steel perfectly fine? Is it a hazardous area where we need explosion proof for general purpose? And then the hardest question is, what's your budget? how much do you want to spend on a meter for the accuracy that you need? And in a lot of cases, the budgets aren't there, so we have to look at a lower cost device. But if the financially, you need a high accurate measurement, mass flow, you can use a density measurement, then that's where we're going to go towards a Coriolis meter. Just ballpark numbers, a 2-inch vortex meter might be in the $3,000 range. A 3-inch or 2-inch, 2-inch vortex might be in about a $3,000 range. A 2-inch mag might be in the $3,000 to $4,000 range. But the 2-inch Coriolis, you might be looking at $15,000, maybe $20,000, depending on the options. So again, there's a big difference in pricing, but with that, you get a lot more information from that flow measurement. So here's a little table we put together. And again, if we looked at the costs, the vortex meters, DP flow, the rotometers, variable area meters, they're on the lower cost side. Mags are a little bit more, but then when we get to, this is the Coriolis and then the inline ultrasonic, they're a little bit more expensive. If we look at, we've rated them what we think as we go, and we're not going to go through all these, but you'll get the presentation and you can do some comparison. And then we have a flow selection poster. So again, if you have a steam application, a magnetic flow meter and ultrasonic, it isn't going to be good for that. If you have an abrasive application, we're going to push you probably towards a magnetic flow meter, assuming it's conductive. If you need a large turn down, magmeter, Coriolis, the ultrasonic, they're all good at meters for that type of application. So this is a flow selection poster that's listed. You can download from our website, or if you contact us, we can send you a version as well. So to talk about some of the installation, first I would say it's not a one-size-fits-all for every technology. Go to the instruction manual, see what for that particular technology, what the requirements are. The old rule of thumb is 10 diameters up and 5 down. And what we mean by that is when we say 10 diameters, if it's a 2-inch pipe, the D would be 2 inches. So we have 10 times 2. So we would need 20 inches upstream and 10 inches downstream. So 10 up and 5 down. That's the old rule of thumb for most technologies, but you'll see some flow meters will require more than that depending on what's upstream of the meter. These illustrations here are of a magnetic flow meter, and most of the installation is 5D, some 10. But if we have a concentric reducer, we're reducing, say, from a 4-inch to a 3-inch line. As long as it's a concentric reducer, we don't need any upstream run. So we can go from the reducer right into the flow meter and then back up to your line size. The most important thing with any flow measurement is making sure you have a full pipe. And in these illustrations, again, it's just making sure you have a full pipe. Flow in the vertical up direction is always the best installation to ensure that the pipe is full. If that's not always possible, if flow has to go in the down direction, just make sure your downstream horizontal is above the meter to ensure that there's enough back pressure to make sure the line is full. And then Coriolis meters, these are probably the most forgiving of all the technologies. You don't need any straight run, upstream or downstream straight runs on the on Coriolis meter. A vertical up is always the best installation. The horizontal is doable as well. If you have a gas application, we want you to install the meter where the tubes are on the top of the line, and that's in case you have any entrained droplets of water. it'll hit the meter, then gravity will help it fall out and it won't affect your measurement too much. For liquids, we want the U shape on the bottom. And that's so if you have any entrained gas coming through the meter, the tubes are filled with liquid and the gas will work its way out quicker. If the tubes are down, the liquid will rise to the top. And then what we never want to see with a Coriolis meter is the meter mounted on its side, because we have the two balanced tubes in there. And if the meter is mounted on its side, as you can see in the picture on the bottom right, if you do have entrained air, the air will typically stay to the top of the line. And now you'll have air through one tube and nothing in the other tube. And it throws the balance of those tubes off, which will greatly affect your measurement.
Okay, thanks, guys. We've been receiving a lot of different questions, and I've been trying to answer them all, but we do have a few more that we'll go through. Before we do that, I'd like to invite you to several events we're going to be attending. We're going to be at the AWWA. This is a water show in California coming up soon in June. We're also going to be at ISA Calgary show, June the 11th through the 13th, and a Hydrogen Technology Expo, which is going to be June the 26th through the 27th. We also have various other trade shows that we'll be at. Please check our website to check those out. Lastly, I'd like to invite you to our next series of Back to Basics, where we unveil the power of visual MESA. This is going to be June the 6th at 2 p.m. You'll be able to register again on our website, and you should be receiving an email after this webinar to also invite you to that Back to Basics series. So now we'll get to a couple of questions here and get Paul and Jim to help us out. Let me get down to the questions. Okay, the first one, can you give us more details on cryogenic liquids, like liquid type, temperature range, special construction on cryogenic?
So our vortex meter, we can do cryogenic applications. Appearance-wise, it looks the same. We have the body and the shetter bar. The shetter bar material is a little different. The piezoelectric crystals inside are a little bit different. And then we do an extension on the neck to keep the head away so you can get insulation around the meter if necessary. We can also use a Coriolis for cryogenic applications. That's a common measurement as well.
Okay. And if the person who asked that question would like more information, just contact us, reach out to us, and we'll provide more information there. Next question is about the vortex meter. Is the vortex meter based on capturing oscillations per frequency, meaning vibration frequency?
So the vortex is, so as the flow is hitting the shetter bar, it's shearing off, it's alternating back and forth. So if you stood on a bridge and you watch the water go past you and you have the pylons there and the bridge, you see a swirl. If it's hitting it perfectly, you'll see an alternating swirl back and forth. Same with the vortex meter, and we're just counting the vortex formation. Again, it's a low pressure area. It's causing the bar to stress from one side to the other, and we're just counting the pulses. Every time a vortice is formed, we're getting a pulse out of the shetter bar, and each pulse is proportional to the flow.
Okay. Next question: do you need to have water vapor pressure if there's a liquid?
It's helpful.
I think that has to do with flashing with the pressure drop.
Yeah.
I think that's what it's geared towards.
Yeah, it's helpful. Back to the cryogenic applications. Having a vapor pressure is very important to because, as Jim said, what vapor pressure in a vortex meter or Coriolis meter, if your line pressure and your vapor pressure and your pressure drop all kind of line up, your process could flash within the flow tube. And that's the point where that liquid is turning into a gas. And that's going to give you very erratic readings. And then what's even worse is downstream, when that gas turns back to a liquid, that's called cavitation. And that's even a bigger problem for you. So yes, knowing a vapor pressure of the liquid is pretty important.
Okay, next question. What is flow span?
So that is pretty much what you want to set your 20 milliamps to.
That is different than the flow range of the device. So you might have a 1-inch mag meter that can measure 0 to 78 gallons per minute. But if the process is never going to exceed 30, you would set your flow span to 30, and that, to Paul's point, that would be what the 20 milliamp signal would represent.
Okay. What is the best flow meter for two-phase flow, liquid and particles, up to 1/2 inch?
I would look at a magnetic flow meter in this case. So I'm assuming it's a liquid with limestone, some type of slurry in there. Definitely a magnetic flow meter. What we do though with the mag meter in these applications is we're going to ask you all those questions, and we want to keep the velocity under 10 feet per second. The lower the velocity, the less slurry noise that's created within the flow tube. And then we may also, even though it may not be necessary, stainless steel electrodes are the most common, but in slurry applications, we may put Hastelloy C, the alloy, which is a Hastelloy equivalent, because that has better characteristics for slurry noise. So, we can do it in a mag, no problem. We just, again, would look at the application and make sure we size the meter properly.
Okay. I have been experiencing flow rate spikes when transitioning from one liquid to another, with different characteristics. What's the best flow meter to use?
Again, if this is a conductive fluid, I don't know why you would be spiking from one fluid to the other. If there is a significant conductivity change from a relatively low conductive fluid to a high conductive fluid, we do have the ability to detect that. If it's a non-conductive fluid, I do not see why that would be the case in a Coriolis bit. I'd be curious what technology you're using that's causing the problem.
Yeah, that's something we may have to reach out to you, get a little bit more info, and evaluate the application and the installation.
Okay, can you discuss more on turn down ratio when selecting a flow meter?
Yeah, so turn down is going to be from the meter's maximum measurable range to the minimum. So for easy math, let's just say the flow meter maximum flow is 100 and the minimum flow is 10. So that has a 10-to-1 turn down. Vortex meters, though, could be as high as 20 to 30-to-1 turn down. Again, that's from the meter's maximum capability down to the minimum. Coriolis and mags could be in the range of 100-to-1. So again, the turn down is from the meter's maximum capability to the minimum capability.
Okay. We got time for one more question. There's a lot of different questions that we didn't get asked. We've got over 40-something questions, so we'll get back to you if we didn't get your question answered. But the last one here is, in low Reynolds number flow, which meter is best?
Yeah, again, we'd have to look at the application. Low Reynolds number typically is low flows. So we can look at a mag meter if it's conductive, Coriolis, ultrasonic. So it just depends on what the application is. It's a low flow, obviously, with low Reynolds number. So we would just have to evaluate the application and see which direction to go in.
Yeah, and again, it depends if it's liquid gas or steam. But at the end of the day, Coriolis have tremendous turn down like mags do. So that's always an option if it's a non-conductive fluid.
Okay. And I'd just like to close here. Thank you for the comments and the Q&A that you sent. One person, great informative webinar. We really appreciate your feedback on that. All the slides will be shared with you. And as soon as this is over with, you'll be receiving a survey. Please give us your comments and let us know how we can continue to improve. Thank you again for your time. Again, the next one's coming up, Back to Basics, will be on June the 6th on Visual Mesa. So we hope to see you there. Thanks and have a great day.